Hey, what's up everyone? I hope you're all healthy and safe wherever you are. Today we're going to make a simulator that's going to help us predict the spread of the coronavirus. But first off, yes, I'm on my roof. And I'm no longer in Botswana. We're back home in South Carolina. It's really weird. You know, one day you're in Botswana, you have all these plans, you got things that you want to do, there's people you're working with, and then you get a letter from the US State Department saying you're coming home as soon as possible, and we're back here. All of you back in Botswana, we miss you. I'm sorry that I didn't get to say a proper goodbye to all of you. I hope all is well with you, and I wish you the best. And of course, these days, everything seems to be about the coronavirus, this COVID-19. That's why I'm on my roof, I guess. That's what you do during a pandemic, right? Actually, we're just staying home, trying not to give or receive any viruses. And all this time sitting at home makes me think, you know, what can I do? There's got to be something I can do. And I got thinking, I'm like, hey, I could write some code. It's kind of a common response for me for a lot of things. But I was thinking, these days I've been hearing a lot of numbers and predictions, and I thought, you know, they don't all match. You know, some people's numbers say one thing, some people's numbers say another. So I thought, let's make our own simulator, and then we can come up with our own numbers. And those numbers might not be as good as the numbers that the World Health Organization or the CDC is using, but they'll be our numbers. And that's kind of cool. And then of course you'll all know how to write your own simulator whenever the need arises. So what is a simulator? It's basically just a computer program that tries to replicate certain conditions or relationships in order to predict what would happen under a certain set of circumstances. Today I want to focus on simulating a pandemic. For this video I'm going to use C++, which is a little different for me. I was just in an object-oriented sort of mood, but I could have used any language for this. I could have used C, Python, Ruby, Perl, whatever. All the source code is available through Patreon. Details below in the description, and a big thanks to all of you that support the channel. I really appreciate it. So now to our simulation. Okay, so today's example is definitely on the longer side. So rather than coding it up as we go, as I often do, I decided to code it up last night, and I'll just walk you through it in this video. Also, I just want to point out that this simulation, like any simulation, has limitations. I'm not a medical doctor, I'm not an epidemiologist, I'm not a COVID-19 expert. I've spoken with a number of doctors. The information in this video does come from conversations that I've had with doctors I know, but in the end, I'm just a computer scientist stuck at home writing some code. So please treat the code accordingly. Okay, so what do we need to do to get started? Anytime you're simulating something, you need to have a good mental model of the situation that you're trying to simulate. We're going to have to make some simplifying assumptions. The simulation is not going to perfectly match reality, but we do need to have a rough idea of how things work in the real world so that we can write code that matches those conditions, because otherwise we're not going to get results that are meaningful. So let's take a look at the code. There are quite a few files here. Let's first start with some building blocks that I'm going to need. I'm going to be simulating people moving around, so I need to have a sense of location. So I'm going to start with a location class. It has two data members, X and Y. It has getters and setters and two constructors, and then a few methods for getting the distance between 2 points, testing to see if those 2 points are the same or close enough, and one that moves a location towards another location. This will be useful once you see how we're moving people around. These are just useful operations that I know I'm going to need. Now, if we look at the corresponding CPP file, this is all pretty straightforward, but I want to point out a few things. First, notice that I'm using arc4 random instead of rand. You could just use rand here. It's just not quite as uniform. I'm actually not sure if it would make a meaningful difference, but I want things to be pretty random here, and I don't want any subtle skew in the random number generator to throw off my results. Notice that my default constructor picks a random location. That might seem a little odd, but for this program, that's what I'm usually going to want, so it makes sense. And of course, I have another constructor in case I want to specify a specific location. The move forward method just moves the location toward the other point using basic trig and the help of our good friend Pythagoras. And this if statement here just keeps us from overshooting a point, so we'll stop at the destination if we hit it while moving towards it. Otherwise, we could overshoot. And the getDistance method just uses the Pythagorean theorem again to compute the distance between 2 points. That's pretty simple. And the test to see if 2 locations are the same uses that function. That may seem a little odd, but floating point numbers are lossy, so they have some precision problems, and so this is safer than using an equivalence test. And you may have noticed that close enough constant was defined up above, and it just needs to be defined to be something really small. And of course, the getters and setters are exactly what you would expect. They just allow me to get the value of x and y and set the value of x and y. Now let's go define some numbers. In simulator.h, notice the if-def guards. You're going to see those in a lot of my headers. If those are unfamiliar, I have a video all about them. I'll link in the description. Go check it out. So first, let's define our world, basically the space we're dealing with. Our simulated people are going to exist on a 5,000 by 5,000 unitless area. Maybe this is meters, I don't know. 5,000 by 5,000, that could be the size of a small town or a big neighborhood. Next, we define the number of hours we're going to simulate and the number of people our town is going to have in it. Next, I'm going to define an enumerated type that's going to represent the states of the disease. Now, I'm definitely oversimplifying here, but in my simulator, people are going to start out as vulnerable, which is pretty much how we all are until our immune systems have seen the new bug that's going around. So initially, we're all vulnerable. Then next, people can be infected, and then they either recover, and if they recover, they develop immunity, or they die. Now, this is certainly an oversimplification, and I'm not sure anyone knows yet exactly how immunity works with COVID-19, but it's a rough approximation of how a lot of viruses work, so for this video, we're going to go with it. For another simplification, I'm going to assume that infections last 20 days from exposure to either immunity or death. In reality, of course, there's going to be some variation here, and you are welcome to change this simulator to add a little bit of variation if that makes you feel better. Next, I'm going to define the probability of contracting the virus after a contact with an infected person. Now, I've heard that COVID-19 is highly contagious, but I have to admit this is a total guess. Once we have things up and running, we can play around with that number if we want and see how it impacts the spread of the disease. So next, we need to define some more morbid numbers. Now, I don't know what the actual fatality rates are for COVID-19. I'm not sure that anyone does at this point, because we really don't know how many untested cases there are out there. There just really haven't been enough tests done, so I don't know if anyone has those numbers, but I'm going to go with 1% here because that's a number that I've seen thrown around. And I also defined a second rate here to represent the higher fatality rate that you'd get when we fill up all the intensive care beds in the hospitals, we saturate our healthcare system, and patients can't get the help they need when they get sick. Again, this number is a total guess. I'm sure it's going to be higher than the baseline number, and of course we can play around with them later to account for our uncertainty, but this is the number I'm going to use for now. Then I define how close you have to be to infect someone. Does 5 meters work? I don't know, I'm just going with it for now. And also how many initial infections we start out with. Now I'm going with 5. We could start out with 1, but I found that it adds a lot of variability to the beginning of the simulation that isn't particularly insightful. It just takes a long time for the infection to really take off. Then I define how many sick patients it will take to saturate the healthcare system. Now this is also a total guess. Not all sick patients are going to need hospitalization, and not all hospitalized patients are going to need ventilators, and not all hospitals are created equal, so this number is going to be different for different towns. For now, I'm just going to say that if 1/5 of the population is sick all at once, we're in trouble. Again, this is a knob we can adjust to match reality in your specific location. And I also define a global Boolean variable to store whether or not the healthcare system is saturated at any given time, and we'll put this to good use later. And then I'm going to be working with a lot of random events, so I also defined this helper function. It's just this try event function, which takes a probability and returns true with that probability and false otherwise. So if I pass in a probability of 0.5, half the time it will return true, and half the time it will return false. And now if we jump over to the CPP file, you can see the saturated variable. It starts out as false, and here is the try event function. And as I mentioned before, it returns true with the probability that we pass in. And it does this by generating a random number across a large range, and then selecting a part of that range that matches the probability we want. Then if the random number falls into that part, then it returns true, otherwise it returns false. Okay, so now we get to our main function. Now notice this is called SimMain, not main. That's really just a product of how I wrote the user interface. We'll get to that later, but if we just wanted text output, then we just change this to main, and of course we'll look at the pretty animations later. But here in SimMain, our simulation is actually pretty simple. We define an array of people and an infection history. Now, you've heard people talking about flattening the curve. Well, this history array, this is the curve for this simulator. It's going to store the number of current infections that there are at each hour in the simulation. And of course, we'll start it all out at 0 using memset. Then we start off by infecting the first 5 people in the array. Sorry, folks. And then we have a loop that's just simply going to go through the hours of our simulation. Now, each time I'm going to refresh the user interface. More about that later. The mod 2 business here is just because all of the drawing was slowing things down and I got sick of waiting, so I decided to skip every other time through the loop. Next, we need to decide how all of the people moved in that hour. That is assuming that they are still alive. Now, just remove this if statement if you want to simulate a zombie apocalypse instead. But for live people, we're going to use a mobility model to move our people around. More about this shortly, but this is just a model that describes how the people are going to move through the space. And we're also going to use this opportunity to let the disease progress. Now, if a person is infected, then this will move them 1 hour closer to either death or becoming immune. Then, once we've moved people around, we're going to go through all the people and see if anyone infects anyone else. We're again only considering living people, and you can't infect yourself. And we're going to look at this try-infect method soon to go over the infection rules, basically how I'm simulating infections. Then we report on the status. I declare some counters. I want to know basically how many people are in each state at each step of the simulation. So we just go through all of the people and see who's dead, who's infected, who's immune, and who's vulnerable. Now, I'm also interested in measuring the peak, basically the maximum number of people infected at once. And we'll check each time to see if the medical system is saturated, and this will impact the fatality rate on the next time through the loop. Then every 10th time through the loop, we're going to print out the counters. That's just to speed things up and so we don't end up with too much output. Then we update the history curve with the number of people infected this time around, and if we get the infections down to 0, we bail. We're done with the simulation because nothing interesting is going to happen after that. The people will move around, but the numbers are just going to stay the same. And then we're all done. We'll print out the peak height, and that's our simulation. At least that's the model part of our simulation. So down here at the bottom is our actual main function, and you notice that it just starts up the user interface, and I'll talk about this shortly. But first I want to talk about the person class and then the mobility models. Okay, in life a person is a complicated thing. In this simulation, not so much. A person just has a location, a mobility model that describes how it moves, a disease status that keeps track of its status, and a counter. And the counter just keeps track of where the patient is in their disease or how much time they have left in their infection. And it also has these methods, and that's going to be our next stop. Let's switch over to the CPP file. You notice our default constructor creates the mobility model. We need to tell the mobility model which person we are so that it can move us around. That basically gives it access to the person. We're going to set the person's initial status to vulnerable, and then set the counter to the number of hours each infection lasts, because we're assuming that each person only gets infected once. If you wanted to add random variation to the infection length, you could do it right here. Now, the infect method is simple. If you're vulnerable, it infects you. Otherwise, you don't change. And try infect, which was the one that we called from SimMain, it's a little more complicated. It first checks to see if the other person is infected. If not, then there's nothing to worry about. Then we see if we're close enough to infect. If not, again, there's nothing to worry about. Then we try to infect this person with the probability we defined previously. So just because you're in close proximity to an infected person doesn't mean you will automatically get the infection. That's how it works in real life. But the longer you hang out with them, the higher that probability will become. The progress disease method does nothing unless you are infected. If you are infected, then it decreases your counter each time it's called. And once you reach 0, we determine which fatality rate you should use based on whether or not the healthcare system is saturated. Then, using the fatality rate, we roll the dice and determine whether the person dies or becomes immune. And finally, the is alive method is super simple. It simply just checks to see if your status is dead. So really nothing too complicated in this file. Now, what about mobility? I don't have a perfect model that describes how people really move, so we're going to just try to come up with something sort of close. I've made a mobility model class. This is just an ancestor class. It's a parent class that's just here to define what a generic mobility model looks like. All mobility models have a pointer to the person that they're moving. It has a constructor, a method to set the person, and then a move method, which is where the interesting stuff really is going to happen. Now, this assign to 0 business might seem odd to some of you who aren't familiar with how C++ handles virtual functions. All this says is that move is not defined here, but must be defined by a subclass that inherits from mobility model. This makes mobility model an abstract class, and this just means that you can't actually make a mobility model. You have to define a subclass and then you can make one of those. And because it's abstract, you'll also notice that the CPP file doesn't have much in it. You're just setting the person being moved. And so let's move on to the subclasses. I made 2 of them. The first is the random waypoint model, which is a super simple model, which I've actually seen used in a lot of different simulations. Basically, with random waypoint, people move at a random speed in a random direction for a random period of time. Now I started with this one because it's simple and it's common, but we're really going long in this video, so it's going to be included in the code, but I really want to focus on my second one because I think it's a little more realistic. Because I don't know about you, but I don't move around randomly in random directions for random periods of time. I tend to go places, and they tend to be the same places that a lot of other people go to stores, to gyms, to churches, to restaurants. We all tend to frequent a small number of places, so I wanted to try to capture that behavior while still keeping things simple, because that seems really relevant to this simulation. So I made another model that I call the popular places model. In this model, we randomly pick a number of locations, and we're going to designate them as popular places. In this case, I chose 15, which seemed reasonable for a small town of 1,000 people. Each person also has a home, randomly chosen of course, and they either go home or they go to one of the popular places. Now, some of these people are social distancing. Right now, it's set to 80%, the rest are not. Those of you not social distancing, you know who you are. Those who are keeping their distance have a high probability of staying home. Those who aren't have a home probability that is much lower, meaning that they're likely to be out visiting a popular place. I've also defined the top speed for our people, basically how far they can move each hour, also the longest amount of time that they can stay at a particular place. Now, the class inherits from mobility model, of course. Each person has a home and a waypoint. The waypoint is just the place that she is trying to get to currently. She also has a speed and a stay, which determines how long she will stay there once she arrives. And of course, their home probability, which is how likely they are to stay home. Now, in the CPP file, we define our array of popular places. Remember that locations are random by default. Then in our constructor, we initialize the speed and select a random home for our person. Then we decide randomly if this person will practice social distancing or not. And we set the probabilities appropriately. Now, when it's time to move, when the move method itself is called, we have 3 different cases that we're going to consider. First, the person might be brand new and not be doing anything. In that case, we place them at home and we pick a new waypoint for them. The second case is when they are at a waypoint and they're hanging out. In this case, we just decrement the stay counter, and when it hits 0, we pick a new waypoint, which will either be home or a popular place. Now, the third case is when we're in transit. In that case, we just move the person along toward wherever they are going. Now, when it's time to pick a new waypoint, we pick a random speed and a random amount of time to stay there. And randomly, depending on our home probability, the person either chooses home as their next destination or a random popular place from the list. And that's all there is to moving people around in this model. We could, of course, get more complicated, but for now, this is what we're going to go with. And of course, it's not a perfect representation of human mobility, but is not bad for 50 lines of code. So after you watch the video, if you want to improve on it, be my guest. You definitely can make any changes that you think will make it more realistic. Okay, so now all that is left is our user interface. The numerical results are, of course, what we're after, but let's face it, simulations are more fun if you can watch things play out in real time. So I made a pretty window that will animate the people as the simulation progresses. So for this, I'm using GTK because it's fairly portable and I already had it on my machine, but there are a lot of different GUI or graphics libraries that I could have used. And today, I just want to apologize in advance. I don't have a lot of time to dig deep into GTK, so I'll see what I can do in future videos, but I'm going to gloss over a lot today. I'm really sorry to all of you who were thinking, yes, he's finally doing a GTK video. Today is not that day. Sorry, folks. So on to my UI. My UI has 2 key functions. The first starts the UI, it handles window creation, and I pass in a function pointer, which is going to be a pointer to my SimMain function, because the UI is going to call that function once the windows are all created. The second function we've already seen, and it just updates the window. If we look in the UI.cpp file, you're going to see that the start UI function does a few things. It creates a new GTK application. It connects a function called activate to the activate signals. Basically, we're just telling it to run that function when the window becomes active, and we're going to pass in our SimMain function to that function so we can eventually call it. Then we run the application, and then once it's done, we clean up after ourselves. Now, when the app starts running, GTK will call my activation function. That's up here. That's going to set up the window, set the title, set the size. It's going to create some space for me to try to draw stuff into, and then it's going to clear the drawing surface. And then once this is all ready, then I'm going to call my SimMain function, which was passed into this activate function. And that's going to start the simulation. So then during the simulation, this UI redraw function gets called after each few simulated hours. And we pass it the list of the people, because they were the ones we're going to draw, as well as the history so that we can graph it. Now in this function, we create a Cairo drawing object, something also I'm glossing over, but this allows us to paint on our surface. And we're going to draw the people, and we're also going to graph the history. And then once we're done, we're going to destroy the drawing object just to clean up after ourselves. Then we mark the window as invalid so that it will get repainted, and this loop down here at the bottom simply checks to see if there are any other events or tasks that need to be handled to keep the window working properly. Now without this, it's likely that our window will either freeze up or not show up at all until the simulation is all done. I think that's actually most likely. And then, of course, we're going to see the end result, but that's not the point. We wanted to see it unfold as it happens. So we're going to have this loop in here to just handle any events and signals and deliver them properly. Now, the draw person function and draw history bar functions basically just set colors and draw rectangles where I want them to. And there are a few other functions here that basically take the image that I've drawn on this Cairo surface and put it on the window. And now that's really our simulator. So I made a pretty straightforward makefile for it, nothing fancy there. And now we can compile it and run it. And you can see that it runs. It pops up this nice little window, and you can see all the little square people moving around following their little mobility model. I'm coloring them based on their status, so black means vulnerable. Those are the people that have never been infected. Green squares are infected people, blue is for immune people, and red shows those that have died. Also, over on the right side, it shows how many people are infected at any given time. So this is basically graphing the infection curve. And this line will turn red whenever the level goes above the saturation threshold. Also note that down here in the terminal, you can see the text output. So this is also showing you how many people are in each category right now. And for convenience, it shows the percentage fatality rate to the right, just to put those numbers into perspective. For this particular example, as we're nearing the end, you can see that just over half of the population eventually got the virus. 1.1% of the population died. But keep in mind that not every run is going to be the same. To show this, let me just run this again, and you're going to see that it provides a pretty different curve. This time we had fewer infections, a much lower fatality rate, and our highest infection rate was 97 people at once. And that's because there's a lot of randomization going on in here, so before I make any conclusions about what any of these runs mean, I recommend that you run it a few times just to make sure that you're not seeing some sort of random fluke. Now, so far we have been looking at examples where most of the population is limiting their mobility. Basically, most people are social distancing, but what happens if they don't? What happens if only, let's say, 20% of the population are careful and try to keep themselves away from other people? Well, let's recompile it and we run it. And as you might expect, with people moving around a lot more, things get out of hand much more quickly. So now at the peak, we have over half the town is infected at once. We've basically saturated the health system very early, so people won't be able to get the care they need, and the fatality rate will naturally increase. And then of course things come back down, and I guess the only real upside of this scenario is that it's over quickly. But nearly everyone in the town was infected. 3.6% of the population died, which may not seem like a lot, but if 3.6% of the US population died, that would be almost 12 million people. But just to make sure it's not a fluke, let's run it again, because this might have just been a random worst case. But yeah, this time the pattern is looking about the same. The peak is actually a little bit higher than before, and yes, when we're all done, our fatality rate was 4.2%. So I will leave it to you to run a large number of trials to determine if the difference is significant or not, but it looks like it probably is. And of course, we can take things to the extreme and see what happens if nobody limits their mobility. And the first time it's bad, it actually looks pretty close to the 20% cases we saw before. We ended up with a fatality rate of 3.8%. So let's try it again. And that follows the same pattern and gives us our highest fatality rate yet. Again, we'd have to run it quite a few more times to draw any conclusions, but I suspect that it will be the worst of the bunch. That would make sense. And for completeness sake, let's try it with 100% distancing. Basically, everyone is following social distancing and staying home as much as possible. And this is usually rather uninteresting. Basically, nobody moves very much, and the infection usually doesn't have a chance to get off the ground. It just dies out really quickly. And wouldn't that be nice if that happened in real life? Now, keep in mind that so far I've just been playing around with the distancing probability, which is good because now when you hear someone really frustrated say, I just drove through town and so many people are out and having barbecues, and I mean, what's the good of social distancing if only half of us are actually doing it? Well, now you can say, well, actually, I've had some time on my hands while I've been social distancing, and I ran some simulations, and that 50% actually matters. And then you can insert the numbers from your own simulations, and you can impress your friends. You can, of course, play around with the other numbers like the infection probability or the number of days the infections last, just to see how those parameters might impact the course of the pandemic. But that is, I think, a good place to stop for today. I hope this was helpful. I hope it helps you simulate either this pandemic, some other pandemic, or something else useful in your life. Once again, the code is available through Patreon if you want to download it, play around with it, be my guest. So thanks for watching. Stay safe and healthy wherever you are, and I'll see you in my next video.